right, so here is the beginning of 9.4. 9.4 is about partial fraction decomposition, which basically is saying if you have a fraction that's a polynomial over a polynomial, we can break it up into other, into multiple fractions. So where the denominators are factors of the original denominator. So each of the new denominators is going to be a factor of the old denominator. Essentially, this is kind of the opposite of what we did back in Algebra 2 with rational equations, where we were adding and subtracting rational expressions, which is a polynomial over a polynomial, right? When we're adding and subtracting those, this is essentially the undoing of that. So we're expanding one rational expression into multiple rational expressions. So let's do an example of what I'm talking about. So say you're given this rational expression, 3x over x plus 2 times x minus 1. We want to split that up into two fractions where one fraction has x plus 2 in the denominator and the other fraction has x plus 1. So x minus 1. So in each of these, you're going to split it up into fractions so that each fraction has one of the factors as a denominator. That's assuming that none of these factors are repeated. I will talk about what happens when you have like a squared here or something. I'm going to talk about that in a later example. But for when none of them are repeated, you're going to have a fraction for each factor. And then in the numerators, you're just going to put generic letters. So A, B, C, D, however many fractions you have. So here we have two fractions, we have A and B, and so our goal is to find out what A and B would make this a true statement, right? Would make these equal to each other. So we're taking one fraction, we're splitting it up into multiple fractions. And so how we're going to do that is the first step. The first step is to set up this equality, right? We're taking the fraction we were giving and we're setting it equal to something over one of the factors plus something over the other factor. And then we are going to multiply the whole thing by the common denominator, or I should say by the original denominator. So we're going to multiply the whole thing by the original denominator. That's always going to be our first step. So they've done that here. And so you can see that if I multiply this fraction by its denominator, obviously they're going to cancel completely. And we're just going to end up with the numerator on this side, which since we're multiplying by the original denominator, that's always going to happen, right? You're always just going to end up with the numerator on this side. On this side is where things get a little bit more complicated. So if we're multiplying by the original denominator, then one of the factors will cancel, right? The one that matches will cancel. And so then we'll have A times the other factor. And then here the matching factors cancel and we have B times the other factor. So it's kind of the setup of what this is going to look like. And then we are going to distribute our A and our B. So we have 3x equals AX minus A plus BX plus 2B. And then the next step, we are going to rearrange it. I'm going to write the intermediate steps here. We're going to rearrange it so that we have the x's together and the things that don't have x's together. Only the things that are already on the right side, though. We're going to leave what's on the left. We're going to leave that on the left. So we have 3x, we're leaving that alone. And we're going to put the things with x's together and the things without x's together. Okay? And then we're going to factor out the x. So that's why we wanted to put them together so that we could factor out that x. So we have x times a plus b, and then minus a plus 2b. And now the logic here is that whatever is with the x on this side of the equal sign has to equal what's with the x on this side of the equal sign. And hopefully that makes sense to you, right? If I have two things that are being multiplied by x, and I want them to be equal to each other, then the things that are being multiplied need to be equal to each other, right? So this has to equal the coefficient of x on this side, and then whatever's doesn't have an x has to equal the constant on this side. We don't have a constant on this side, so it's going to have to equal 0. So a plus b has to equal 3, and negative a plus 2b has to equal 0, because there is no constant on this side. So we end up with having two equations. And now you might be seeing why this is coming up in a lesson on systems of equations, because we're going to end up with a system of equations. So a plus b has to equal 3, and negative a plus 2b has to equal 0. So we end up with this system of two equations with two unknowns. And then we're going to use elimination to solve for a and b. So we already have a and negative a, so we can just add those together, which will get rid of a. So we end up with 3 on this side, 3b on this side. If we divide by 3, we end up with b equals 1. So we're just solving it like a system of equations. We end up with b equals 1. We can plug that back into either one of these. So if I have b equals 1, I have 3 equals a plus 1. So if you subtract, then I have 2 equals a. So I have b equals 1 and a equals 2. So my answer, remember the whole point of this was to figure out what fractions would equal our original fraction. So my answer is 2 over x plus 2 plus negative 1, or you could just do minus 1 over x minus 1. So this is my solution. So just telling me a equals 2 and b equals 1. Oh, b equaled positive 1, not negative 1. Sorry. Whoopsies, my bad. Just telling me that a equals 2 and b equals 1 is not enough. This is your solution. It needs to be in this form with the fractions. So that's partial fraction decomposition. That's the main strategy, and we're going to be doing a couple more examples with that in the next couple of videos, and I will see you there.